MET 345 Test 4 Review. First off, we have critical processes attending heavy banded snowfall, that section. First of all, we're going to define the four types of stability discussed, and those include conditional and convective instability, and then inertial and conditional symmetric instability. Those first two, conditional and convective instability, are gravitational, meaning that they're vertical, while the other two are horizontal. Conditional instability is that thing we learned in 260, if you recall correctly, where the environmental lapse rate differs depending on if the environment is saturated or dry. And a parcel's stability depends on whether the environment is saturated or dry. Hence the conditions, conditional instability. And it's based on the parcel. If the surroundings are saturated, the parcel will keep rising, and if not, the parcel will sink. Convective instability occurs when theta decreases with height, meaning that air becomes colder and drier with height, like an area under the DCB, the dry conveyor belt. Inertial instability is just the horizontal version of gravitational instability, basically. I.e., if a parcel is displaced horizontal from its geostrophically balanced base state, will it return to its original position, or will it accelerate further from that position? Remember, this is how Rossby waves worked. And then conditional symmetric instability. This states that a parcel is stable with respect to the horizontal and vertical motions, but is unstable with respect to slantwise motions. So this is a very special case. And large-scale lift and saturation must be present to realize this sort of instability. And the presence of both conditional symmetric, inertial, and convective instability are indicated where equivalent potential vorticity, or EPV, is less than 0 potential vorticity units. So here I'll be describing the drawing of a conceptual model for heavy banded snowfall in the central US, and you might want to follow along in the study guide as I do that. But I'll be describing it here as well. Warm air comes up from the south, and the low causes large-scale lifting. Frontogenesis causes it to be mesoscale, becoming narrower like a front. And if it's far enough north, it will be cold enough for snow, and because it's narrow, it will be snow banding. So here's some factors that will contribute to banded snow. Development of the trowel airstream, mid-level frontogenical circulation, reduction of moist static stability, meaning decreasing EPV, relatively deep layer moisture to the northwest of the extratropical cyclone. And all of these features just described are related to the warm, cold, and dry conveyor belts, which can only be visualized through system relative flow analysis on isentropic surfaces or atmospheric trajectories. Banded snow can be difficult to predict for forecasters because you have to look for frontogenesis, instability, and moisture, and they all have to be on the same spot. So next we'll be covering severe weather climatology and severe weather definitions. So you're going to have to know all these definitions for the test that I'm about to read out. So a severe thunderstorm is a thunderstorm which produces tornadoes, hail at least 1 inch in diameter, or winds of 50 knots or greater. Just one of those classifies it as a thunderstorm. A mesoscale convective system is a precipitation system having a spatial scale of 20 to 500 kilometers and a temporal scale of 2 to 12 hours that indicates convective during part of its lifetime. A complex of thunderstorms which becomes organized on a larger than individual thunderstorm scale, and it normally persists for several hours or more. MCSs may be round or linear in shape and include tropical cyclones, squall lines, and MCCs. MCS is often used to describe a cluster of thunderstorms that does not satisfy the size, shape, or duration criteria of an MCC. Propagation is a component of storm motion which is a result of preferred new cell development on one flank, usually on the right or right rear of the updraft. The outflow boundary is a storm scale or mesoscale boundary separating thunderstorm cooled air from the surrounding air, similar in effect to a cold front. Passage is marked by a wind shift and usually a drop in temperature. Outflow boundaries may persist from 24 hours or more after thunderstorms that generated them dissipate, and may travel hundreds of miles from their area of origin. New thunderstorms often develop along outflow boundaries, especially near the point of intersection with another boundary. Next, we have a derecho. A derecho is a widespread and usually fast-moving windstorm associated with convection, and they may include any family of downburst clusters produced by an extratropical mesoscale convective system, and can produce damaging straight-line winds over areas of kilometers long and more than 160 kilometers across. An enhanced V is a pattern seen on satellite infrared imagery of thunderstorms in which a thunderstorm anvil exhibits a V-shaped region of colder cloud tops extending downwind from the thunderstorm core. The enhanced V indicates a strong updraft and therefore higher potential for severe weather, and the enhanced V should not be confused with a V-notch, which is a radar signature. Speaking of a V-notch, it's a radar reflectivity signature seen as a V-shaped notch in the downward part of a thunderstorm echo. The V-notch is often seen on supercells and is thought to be a sign of diverging flow around the main storm updraft, hence a very strong updraft. This term should not be confused with inflow notch or enhanced V, although the latter is believed to be formed by a similar process. Finally, we have the inflow notch. Inflow notch is a radar signature categorized by an indentation on the reflectivity pattern on the inflow side of the storm. An indentation often is V-shaped, but this term should not be confused with V-notch. Supercell thunderstorms often exhibit inflow notches, usually to the right quadrant of a classic supercell, but sometimes in the eastern part of an HP supercell or in the rear part of a storm, in which case it's a rear inflow notch. So, now we're going to cover how we interpret climatology. Why do we interpret events occurring within 25 miles of a given location? We interpret it this way because using a very specific location, such as your house, will result in almost no reports ever being shown there. For example, the chance of a tornado striking specifically your house in the same location more than once in the course of 30 years is almost zero. We put reports in an 80 kilometer by 80 kilometer grid, and if one or more reports occur in the grid box, the box is given a value of 1. Otherwise, the value is 0. The frequency of severe weather events is found by number of 1 that I just mentioned divided by the number of years for the period. And you get a normal distribution when you do this. So next I'm going to go over the specific areas where things might occur, and I'll say those things as we go. So for tornadoes, these occur between usually October and February and have low values for Dixie Alley. There are particularly strong trails, but maybe underrepresented by lack of population. But they're also, of course, prominent in Tornado Alley, which is the Great Plains region. For strong winds, you'll usually see strong winds in a mesoscale convective system, an MCS, between 50 and 64 knots for the eastern U.S. And you'll see winds of greater than 64 knots for the Great Plains from supercells or MCSs or derechos. For hail, you'll see large hail in the central U.S. because of the steep lapse rate. So, climatology for tornadoes. From March to April, the probability increases and they move west, and May is the most intense time in Tornado Alley. However, tornadoes shift into the northern plains in June and July because of increased moisture available from crops such as corn. Next, we'll talk about MCSs, their initiation, their conceptual structure, their propagation, and their dissipation. So, an MCS, as we've discussed, stands for a mesoscale convective system. And we're going to compare the characteristics of eastern and western MCSs. So remember that the boundary that separates them is the Mississippi River. So MCSs that are east of the Mississippi River are eastern, and western are western. So the characteristics of western MCSs. Western MCSs are formed by convective feedback, dryline activity, and orographic effects. 75% of them form overnight, and their convection is modulated by the low-level jet in the Midwest. They have higher cloud bases and higher CAPE values. Often, convection is capped early and explosively develops later. And convection often behaves in a more independent manner than MCSs and eastern MCSs, independent of large-scale flow. And for eastern MCSs, they're formed by warm frontal systems, shortwave forcing, sea breeze, and tropical systems. 75% of them form during the day, and their convection is modulated by diurnal heating. They have lower cloud bases and lower CAPE values and higher frequency of heavy precipitation rates due to deep layers of moisture. They have less dry air inserted to them than their western counterparts as well. The aggregate precipitation area in the east is almost as large as that in the west, despite smaller area in the east. So next I'm going to be reading out the flows and pressure systems seen in a cross-section of a typical mature MCS. And I recommend that you go along on this graphic on the study guide while listening to this portion. So, L1 on the graphic is a wake low associated with adiabatic warming from unsaturated descending rear inflow along the back edge of an enhanced stratiform rain region. It is a mesoscale low and dry air sinks and warms here. L3 is a Limon low associated with latent heat release in the sloping warm updrafts and dynamic effects of accelerated front to rear flow. And this is caused by latent heat due to condensation. L4 is a mid-level mesolow, and it's larger in scale and associated with latent heat release in buoyant traveling anvil clouds. L3 and L4 are responsible for mid-level rear inflow jets. Next we have H1, which is a mesohigh, and it's associated with precipitation drag and evaporation which produce the cold pool. This is a thunderstorm high and it's long-lived. Evaporation here causes cooling, which adds to the high pressure. And when the rain is falling, it pulls down air with it, adding to the high pressure as well. H2 is an upper-level mesohigh, and it's shallow and short-lived and forms due to divergence production aloft. More prominent in mesoscale convective complexes. And finally, L2 is a weak mesolow, and it's ahead of the convective line at the surface associated with warming by compensating downward motion. And this is a rarer kind of low. So next on the study guide is a diagram of the mesoscale convective system's evolution. I'm not going to describe it here. You might just want to go onto the study guide and look at that. However, concerning the graphic that involves what takes place between the cold pool and low-level wind shear, I will describe that. And this is for a more short-lived MCS, and this is descending rear inflow. So here, the cold pool quickly dominates over the weak shear from the west, and the weak shear will result in rapid mixing of the updraft with rain-cooled air in the center of the cloud, resulting in a lukewarm updraft. This will decrease the in-cloud buoyancy gradients, allowing the cold pool to dominate over the shear. And the cold pool circulation pulls the rear inflow jet down to the surface, which is a characteristic of a decaying storm. The rear inflow jet is too weak, and it gets pushed down by the precipitation. Here, however, we have a long-lived MCS with larger wind shear. And with stronger shear, the cold pool will not disrupt the in-cloud buoyancy gradients as much, resulting in a more upright updraft that does not mix with the rain-cooled air in the center of the cloud. And the in-cloud and subcloud circulations in the rear of the storm will be in balance, resulting in an elevated rear inflow jet, a signature of a stronger storm in its mature stage. Here, the rear inflow jet is stronger for longer and does not cut off the updraft flow at the bottom of the storm, which is what is powering it. So, next I'll explain the significance of a rear inflow jet in the context of a cold pool shear interaction. So the rear inflow jet causes downdraft winds to be more intense. Because it's higher up, it needs to go somewhere, so it goes down. Remember that an updraft will always end up leading to a downdraft somehow. Because it's elevated, it lives longer and is not cutting off the inflow, which then becomes an updraft. The rear inflow jet is a result of shear, and stronger shear means a stronger jet. And precip makes the cold pool, which decays a storm. When in balance, the shear versus cold pool is elevated. Eventually, the cold pool wins and the jet goes down and the storm dies. Eventually. So what's the difference between discrete and continuous propagation? For discrete propagation, it's a propagation that involves the development of new cells produced from enhanced convergence in the boundary layer caused by downdrafts from the main storm. And the new cells here usually form 4 to 10 kilometers away from the main storm and then merge with it afterward. And the mergers usually produce an increase in total storm area. Multicellular storms tend to propagate by discrete propagation, whereas continuous propagation is a form of propagation where newly formed cells and their associated updraft continuously feed the main updraft of the main storm, rather than providing for the growth of new cells. Supercell storms tend to propagate by continuous propagation. Next, we'll go over a little bit of Corfiti vectors that you really want to watch along in the study guide while I do this. So, I'm going to go over the examples drawn on the study guide. And remember that Corfiti vectors are a tool that can be used to help predict the motion of an MCS. So for upwind propagating, it's caused by the low-level jet, where the white in this drawing is the actual wind. Blue is the negative version of the low-level jet, which remember just reverses the direction of a vector. And red is the movement of the center of the storm. And because the storm is drifting southwest, because the low-level jet is adding more onto the storm. For downwind propagating, it's caused by dry air and it's a more forward propagation. The white arrow is the actual wind and the red arrow is from the previous diagram. The green arrow is the movement of the storm center if there is dry air and forward propagation. Note that the downwind is moving faster than the upwind because the arrow is bigger. Backwind propagating MCSs appear to move backward as the centroid moves backward. And some properties of backward propagating quasi-stationary MCSs include the maximum CAPE values are along and upstream from the MCS. There's a ridge of theta E along and upstream from the MCS. There's a quasi-stationary west to east boundary present. The mean winds from 850 to 300 millibars are weak. The low-level jet is upstream from the MCS location. There's a difluent thickness pattern aloft from about 850 to 300 millibars again. And there's typically an upper-level ridge aloft. Veering winds with height dominate speed shear, meaning that winds vary more directionally with height rather than by speed. And the strongest moisture transport and low-level moisture convergence is located upstream from the MCS. So, for the forward propagating MCS, the centroid propagates forward. And some characteristics of that include the maximum CAPE values are downstream or coincident with the MCS. The 850 millibar theta E ridge is downstream or coincident with the MCS. There are moderate to strong 850, 350 millibar mean winds, and the low-level jet is coincident with the MCS location. There's a progressive south or west trough translating eastward. And the 300 millibar upper-level jet is oriented west to east and is positioned north of the MCS, and the strongest moisture transport and lowest level moisture convergence is located along downstream from the MCS. Basically, for these, you can just think about what things are going to produce a storm and then think about where they are relative to the storm. So obviously, if a storm's quote-unquote propagating backward, then the things that produce it have to be upstream from it. Otherwise, it wouldn't propagate backward. It'd propagate downward or forward. So then we have MCS maintenance probability, which is essentially just the probability that the MCS will continue for a certain amount of time. And the four best predictors for this are maximum shear, the 3 to 8 kilometer lapse rate, the moist unstable parcel CAPE values, and the 3 to 12 kilometer mean wind. Almost all of this can just be summarized as moisture lift and instability, however, and shear. With this probability, it can help us discriminate between mature and weakening MCSs. And MCS speed probability is the probability that an MCS will move with speeds greater than 18 meters per second at maturity. And There are three good predictors for this, which are normalized maximum vertical difference in theta e between low and mid levels, 2 to 12 kilometer mean wind speed, and normalized 2 to 6 kilometer lapse rate.